thermal limits. In this, in fact, the thermal balance is being influenced by two main factors. The first factor is the heat that is coming for the current flowing inside the component. And the second factor describes how the surrounding medium has the ability to decrease that heat. In particular, the maximum capacity, the maximum current that could flow inside the component is proportional to the delta in between the temperature of the ambient and the maximum temperature of the components. So, means if the ambient of the temperature started to increase, the capacity will decrease. However, climate projections point out that the temperature of the ambient will increase, probably will increase in the next day. Meaning so that now that this delta for 2050 will be smaller than 2030. But however, we don't know how much it's going to be. So that raises my first question. How can we project reliable thermal limit for the next decades? Before we start to explain a little bit the method, let me explain three fundamental concepts in this investigation. The first is the ampacity. The ampacity is the real maximum current that a component can carry out safely. So could be calculated or monitored. And here you will see it in blue. The second is the rating. The main difference in between ratings and ampacity is that the rating is a value selected by the operator. So that means if I have a really conservative rating here, we could be under any physics. However, if I select more dynamic rating, I could be in a risky zone. So how can the transmission capacity could be extended safely? In order to address this, over 3 decades before, a concept of dynamic ratings has been existed. This concept is mainly related with the weather-dependent ampacity, so the use of this, and a component a lower maximum capacity allowed by the operator. So the second one. However, this concept is mainly related with short term. So that raises a challenge. How to develop in advance thermal ratings without compromising safety? So now we establish the fundamental concept. Now let me show you the full landscape of the context. This table that you see here is mainly divided by the three main components that this research investigates and the main subjects of the research. So let me explain a little bit. Here in the first column, we could see that the thermal models are really well established and standardized. Second, we see that mostly all of the work have been done for overhead lines. And the third, that this work have been doing for short-term operational planning. So that let me show clear methodology of that. First, your studies integrate dynamic thermal rating with the long-term plan. Second, there is no standardizing method to include dynamic weather ratings with risk-aware planning. And the third one, and the most important one, also the climate change are not directly influenced inside the rating. So now that you could see here all of the landscape of my research, let me show you the key studies. So it's important to highlight that there are really studies that understand or analyze the interconnection between climate change and capacity. The first one is Bartos. Bartos analyzed all the weather lines in the United States using representative concentration pattern. He found out that the capacity in mean in the United States would be reduced to 6% by 2050. The second study is in UK. Cadre analyzed the overhead lines using 100 weather generator scenarios for 2050. She found out that, for example, for the month of summer in 2050 will decrease the capacity. The third study that I showed you here is a study that not only analyzes the capacity of the component, but also the penetration of PV. We find out that using representative concentration pathway, the business as usual scenario over 2,100, the PV could increase by the use of TTR over 45%. However, as you can see here, all of these studies have been focused in overhead lines. And probably there are not fully represented climates. So in that, can we fully represent the future climate in order to analyze the capacity of power system all the components? The second study is related with DTR with probabilistics. The first study is a study in overhead lines made by Lewis. The important part of this study is that he released a new concept of DTR. It's called quasi-dynamic rating. So, in order to do that, he introduced cumulative distribution functions inside the ratings in order to let the operator introduce the risk. The second is a probabilistic management of the risk. So, here, Bracali introduce a probabilistic forecast for demand and generators in order to control the risk inside the power transformer. He found out that doing this methodology, it could reduce the economic losses over 65%. The last one is a method that also uses cumulative distributions as Douglas, but this time, he selects a time-based subset for the time. So that means that now you have the possibility to select monthly, hour, frequently. We find out that using this, the capacity will increase over 33%, meanwhile controlling the risk. So now, beyond studies that analyze the capacity, we need to see how is the rating increased with the risk, however. The first is Badger. Badger introduced a robust control inside the rating using a probabilistic constraint. So he found out that doing this, the cost could be reduced over 8%. The last two papers are related in how to introduce the thermal balance inside the constraints of the optimizations. So Lee and Kirikelko shows that when you start introducing in order to control the maximal temperature of the component, even in extreme weather, could be reduced over 1% the cost. However, all of these investigations have been focused in overhead lines and in short term. So all these insights shapes my contribution objective. The main objective of my thesis is to develop a methodology for long-term power system planning that incorporates the interrelationship of three main concepts: thermal ratings, network planning, and climate change. It will be addressed by 6 questions. The first question is in order to know how to calculate the thermal rating in advance, including variability and capacity. The second is the next 2 questions are related to how to introduce these ratings inside the network planning. And the third one, how will be the climate change impact using the previous 4.1. So until here, we have established the context and the main question of my research. The following slides will be focusing only answer one question: how we could calculate in advance the rating for the next decade. So first, we need to. It's important to highlight that in order to calculate the ratings, first we need to calculate the capacity. And in order to calculate the capacity, we need to use thermal models. And here is the most used and the most studied one is the thermal model for overhead line. That is mainly governed by the thermal balance and is influenced by the temperature of the ambient, solar radiation, and wind speed. However, as we know, overhead lines could be extended for many kilometers. So, in order to address this methodology analyze the spatial variability of each segment inside the line in order to find the worst condition. The next thermal model that I'm showing you here is the underground curves. The main difference in between the underground cables and overhead lines is that now the heat exchange is occurs with the soil. The second is that mainly this component is installed over 80 centimeters and even to 5 meters. And the third, that the thermal balance formulation is mainly influenced by the soil temperature and soil moisture. However, this thermal model has a challenge in between. We need to find a resolution for these two across different regions in order to calculate it. So, in order to understand this, first it's important to highlight that the physics behind the temperature of the soil and the moisture of the soil are non-linear and complex. And mainly is influenced by the soil temperature and sulfate methodology. So, in trying to find the data in order to model this, it's not an easy task. For that, I use my first method of even solution. I will see here in one thing that into soil classification and sulfate methodology in order to predict the soil of the temperature and moisture. And now we have the opportunity to calculate the thermal resistance of the surrounding soil across regions and across time. For that means that if the operator wants to calculate the capacity of the example, they use it for the next decades. Now we have our last thermal model, is the power component. This thermal model is really influenced by the solar radiation and the temperature climate. And the key factor here is the minimum factor. So here we use well-known and standard in order to calculate capacity. However, it's mainly modified in order to introduce the influence of the solar radiation. So, at the beginning, we will how to calculate capacity by the use of thermal model and the weather. And still, I didn't answer the question. How are you going to calculate in advance? The current system is like thermal methodology. And if we focus in a trade-off in between maximization of the transmission capacity, meanwhile controlling the things. So, let me tell how I do it. It's a five-step step. The first, for the specific location of the conflict, I gather the only methodological variables. Second, by the use of the specific thermal model, for example, over the line, I'm going to calculate the capacity. So here, in this specific figure, you see the calculation of the capacity over 50 years. After we have all the simulation, now we have the possibility to divide it by specific temporal subsets. For example, 1 hour, 1 to year. With that, we are going to focus in the low detail of the distribution of the subset in order to gather the experience. So, let me show you here the picture. Here we have a 4-year capacity calculations. Here, each color is a subset. Here is monthly. And in this subset, we focus in the low detail. So you see the red dots. Now, with this observation, we have the possibility to fit it inside the power law. This is mainly because using that, we could use a lower threshold limit that will be related with to limit exposure to extreme climatic events. So, now this represents here, we are going to feed the result that you see in the blue dash. So, here, we have a periodic distribution for temporal subset. So with this, and with a specific lower threshold that could be 1,000, we fulfill our quasi-dynamic thermal ratings. So let me explain a little more this figure because it's important. So here we have an example of ratings that in order to build this, we use a subset monthly hour. So I will describe monthly hour. In that, we specific a low threshold that is going to be 1 per 1,000, and with this threshold, we could build different ranges across months and across hours. So now we will represent the whole year. So another thing that you see here is the seasonality. that government and rating. Furthermore, reviewing credit and fee control. So,
because of the problem of the sound,
yes,
time on the 45 minutes. Can you try to don't use this one and speak close to this?
Of course.
Because if
Is echo?
yes, maybe you
Pero
don't
close? I cannot move from here.
One second. First of all, let's see if they hear.
Hello? Professors?
Yes, it's much better when you use the this one.
Okay, let's do like this then.
So I'm gonna stay here.
Yes, please.
I'm not gonna move.
Yes.
Sorry for the.
No.
I will do like this, okay?
The audio visual.
Okay, sorry. This is research.
I'm gonna have to show.
So until now, going back, until now we have established how to calculate the ratings in the next decades. And here we find the first result for the first methodological contribution, that is to asset a machine learning model in order to project the soil moisture and the soil temperature. So in order to do that, I trained 5 machine learning models using all the soil composition observations, surface methodology, and observation for 32 stations. With that, we see that with the result of these machine learning models, we also not only improve the variability of the variable, for example, but also we improve the accuracy. So as a result, now we could project also soil temperature and soil moisture for the next 50 years if we want. The second is the QDTR performance. So in order to see the performance, in the left part, we see the trade-off of QDTR, higher rating, lower risk. And here we see the possibility that select different kind of time scales. So let me give you an example. Here we have an overhead line. Here in the previous, in the gray one, we have the results of the opacity. But here is the QDTR calculated in a monthly hour. So now we only not only expand the maximization of the capacity, but also we could reduce this risky zone that could be overheated the component. The second is the thermal performance of the QDTR. So let me explain this slide. We could see 3 things. First, that is time dependent, meaning so that have the possibility to select monthly hour, as I showed you before. The second is the seasonality. Other month, maximization of the rating. Other month, reduce of the exposure to the climate change, to the climate zone. And the third thing that we show here is the difference between models. So underground cables, as you see here, is reduced variability, and it's mainly by the influence of the soil inertia. The third result is a spatial performance of the QDTR. Sorry, I was moving. Of the QDTR. So to do that, we ran the same previous methodology, but this time across Europe. So that means with that 0.25 resolution, and over the last 50 years. With that, we could see some interesting things. First, underground cables rating is mainly strong. It's mainly connected at the strong influence of the soil taxonomy. For that reason, you see all this variability of the ratings. The second, power transformers. There are more pronounced in some regions, the results of the rating, and mainly because, if we remind, this thermal model depends mostly in the ambient of the temperature. So until here, we have the summary of the first chapter. So what was my motivation? I need to calculate in advance the rating. How I did it? 2 contributions. First, in order to gather the information for underground cables, a new model to estimate projections, soil moisture and soil temperature, in order to calculate the thermal resistance. And the second and the most important one is the quasi-dynamic thermal rating. This is not only a methodology, this is a rating description that should be integrated inside the dynamic thermal rating. With this, we could maximize the capacity, for example, 22% in power transformers in a regional way. And second, meanwhile, controlling the risk, because I have to say that all the previous results that you saw is with 1 per 1,000 lower threshold risk. So until now, I established the tool or the methodology in order to calculate the rating interval. The second, in the next slides, I will focus on how to integrate this thermal rating inside the network plan. So here I'm bringing to you a typical network expansion plan formulation as optimization problem. So this optimization aims to reduce, to minimize the system cost. However, it's important to highlight here that it's mainly focused in the control the capex of line and power transformers and no generator. And we did it because we want to. I want to isolate the influence of the QDTR. So a little bit of this here, how it works for each network component. For example, underground cables, overhead lines. I'm going to calculate the QDTR, that's a cumulative distribution, and I'm going to fix a specific lower threshold. As I said, normally all my studies doing with 1 per 1,000. And with that, we're going to replace the maximal limit constraint inside the thermal limit constraint of the optimization. So let's see the results of this. First is the impact of the QDTR using a specific network expansion plan now with the library of PIPs. It's important to say that even PIPs that we managed to simulate to the QDTR over all the regions that you can see here. The way that works with PIPs only let to use QDTR across interconnection, so reduce quantity of lines. For that reason here, you even with that QDTR only interconnection, we visualize that the system cost will be reduced using QDTR with a thinner resolution here in Montreal. The second is in order to overcome the limitation of PIPs, I decided to move to a specific network test case. So as you can see, the 24 nodes here is projected now in the south of France, and is included the QDTR for lines, underground cable, we replace it here, and overhead lines, and analyze it typical 2 cases. So this result is very important. First, because capex reduction. So that meaning that with the use QDTR with a thinner resolution, we don't need to build more lines. However, the second result that now we have a PV penetration, we see that now the QDTR highlighted dangerous zones when we have the probability to have high flow caused by the PV and reduced rating caused by the seasonality. And at the end, that means that we need to build new lines for these 2 consequences. Now we're moving from macro to micro. That meaning that now we analyze the impact of QDTR in lower voltage distribution networks and middle voltage distribution networks. In the future energy transition path, that means that we have now high increase of PV and charging stations. So the result here in the case A is that using the QDTR with a thinner resolution, we could reduce the total violations by night times. You know, when the people arrive home, you need to connect and charge the vehicle. The second, case B and case C is a medium voltage. We see the same result as previously. So that meaning that we confirm that using the QDTR in the cases that only we increase the demand, the investment is reduced, so no lines. But also, when we use QDTR, when we have high penetration of PV, we highlight and identify dangerous situations. And at the end, it will end in a new investment inside the lines. So we need to make a stop here is because all the calculations that you have seen before, I need to highlight that have been with QDTR. And the QDTR, in order to calculate it, we remember the thermal balance equation is mainly with maximum continuous loading and a fixed threshold, 1 per 1,000. However, this is too conservative. So that kind of detail is mainly what my investigation want to overcome. So for that reason, it's coming my third methodological contribution. That is a more precise temperature-based constraint method. So let me explain this title. So as a QDTR, the component should be worked always in the safe zone. The safe zone is below temperature maximum. However, it's possible by a few hours extend this zone to a tolerated risk zone by a delta of temperature. So now the component not only could work here, that is our conservative area, but could be extended in a small area here in a yellow. If it's working in the red shadow, meaning that now the component has the high probability to reduce the lifespan or compromise the safety. So I'm going to explain it more in detail. So for now, we are going to, in order to that, we calculate the cumulative distribution for a specific line in order to gather all the current flowing. For each values of the cumulative distribution in that specific line, for example, we are going to use and remember our thermal balance equation, gather the information of the weather and the rating in order to calculate the temperature. So now with a different sets of a specific weather related with that specific point, we're going to calculate the temperature. And we do that for all the current distribution. With that result, we could build our cumulative distribution of the temperature that you see here in yellow. However, if the result is not this yellow, is this yellow shadow one, meaning that now we are in the risk zone, a control should be done, and the control is reduce the rate. So from the graph, we are coming to a flow. So let me explain the same methodology now with a flow. From a specific scenario input, we calculate the QDTR plus a delta temperature for each time step. For each time step, we are going to run Monte Carlos using optimal power flow plus optimal power flows with contingencies. With that information, the result of the Monte Carlo, we could build density functions. So here, for example, we see the density function result of the power flow normal. And all these are the density functions of each contingency over the line. Why we do that? Because now with that, we're using a specific weighted density function, we could calculate our final current density function. Why we need that? Because with that, we could use the cumulative distribution in order with a set specific temperature in order to calculate the risk. So at the end, if the risk is in the no risk zone, the rating will be replaced inside the network plan. If not, we need to reduce the rating and start again the procedure. I need to remind that this procedure also we use auto sample in order to clarify that the results is correct. So let me show the results of this methodology. So for this, we use our test case. It's similar test case, but this time with our risk management control, and the optimization will be expanded a little bit in order to include a multi-period optimization. So we have the results, but before I need to explain a little bit this chart. Left columns are QDTR calculated yearly in the time yearly. Right column, QDTR calculated monthly hour. Yellow results means the results of the use of a static thermal rating. The conservative that say that we need to use 40 degrees, for example, as the temperature. And the second is the power flow as a result for the QDTR yearly using the methodology that I showed you before. So 3 behaviors to show here. First behavior, in specific lines, by the use of the QDTR yearly, we show the same contribution that I showed you before, reduction on the investment completely. It's not necessary to do an investment, a new line in this specific line. But the second behavior is more complex. It's showing that using the static thermal rating in another line, because it's the 18 and 22, we need a new investment. But here, the rating starts with a specific calculation, but before the investment, it's going to be constrained so enough to be held until 2040, and 2040, we need a new investment. So here, we delay the investment using the QDTR with risk control. And the third one is now the same line, but with a thinner resolution of QTTR. So imagine here we delay, and here we start again. We reduce completely the investment, only selecting a thinner resolution of the QTTR. So meaning that when we change thinner resolution, but we include the risk control, we could reduce all the investment over the case. So as a summary, question, how to integrate the QTTR inside the network planning? To answer, first is the first method is going to be introducing the QTTR to replace the rating directly inside the network expansion plan. And the second, temperature-based, more constrained method in order to calculate it, the rating. To highlight, we use this case in different network expansion planning, and we found similar results, meaning that showing the performance of the QTTR. And the last, that if we use the risk control, we could delay investment and also reduce if we change only the resolution inside the QTTR. So until now, we have established how it's going to be the thermal rating methodology, how to introduce it. And now we need to answer a question, how to include the climate change and how it's going to be the impacts. So it's important to highlight that all the calculations that I showed before and every result that I showed before is with historical values. However, if I want to analyze a network today or plan a network today, must work in the next decades. And we know that in the next decade, the temperature is going to rise. So how we found a solution about that? So my framework, my new framework here, introduce all the methods that you saw before, risk control, QTTR. However, we change the data. Now the data is a future data about climatic conditions. For this, we are using a specific data, the climate energy indicator for climate projections, as a proxy or best information available for long-term climate conditions. So let me explain a little bit more this data. So this data is made according to the representative concentration pathway and corresponding to the radioactive forcing that is related with the CO2 emission and the greenhouse gases emission too. So also this data set is important to highlight that have a link with the electrification. So let me explain more about this. So we are going to take as example the business as usual or the worst case representative concentration pathway that is 8.5. In the 8.5, we are going to have high temperatures. If we have high temperatures, meaning that now the power system components is going to be more stressed. However, in this scenario also is included how we are going to make the electrification and how it's going to be the transition of the energy. Meaning that in this scenario, we are going to use more coal and less PV production. So for the side of the flow, the network is going to be less stressed. However, if we took the best one, or the most optimistic one, that is 2.6, it's contrary. We have less impact of the temperature, so less stress at the network by the temperature. However, now we have a higher imposition of the PV and wind, for example. That makes that now the network will be stressed more by the flow. So let's see some results of here. So this beautiful heat map table is divided by 3 columns. Each column is related with a specific power system component projected in the south of France. And each row is a representative concentration pathway that evaluated. So what we could see here, first, is that underground cable is going to be this specific underground cable is going to be the less impacted by the weather, as I told you before, mainly related with the solar inertia. Second, the most impacted one is the power transformers. However, in this specific power transformer are framed by a specific reduction during a specific hour and a specific month of the year, mostly because related with the temperature. And the third one is most of the year, most of the representative constellation pathway, we're gonna have like reduction of the capacity. So the following results, we use the same methodology that you showed before, but now we do it in a continental case. We use the RCPs in order to calculate how it's going to be the QTTR in 3 main components. So the same structure. What we can see here as a regional pattern before wasn't a specific power system. This is regional pattern. As a regional pattern, we see that the low impacted still is the underground cable, confirming the hypothesis. Second, that the power transformer are the more stressed about the climate, even to 5.5. But however, as I say, we could see that some region, for example, south of France, the south of Spain, will be more impacted than other regions. And mainly because, as I said before, is influenced mainly about the temperature of the animal. And the third thing that we see here, that all cases we saw reduction. So that meaning the climate will reduce in different scales, but will reduce the capacity of the network. And now we analyze how it's going to be the climate impact in system cost. So we use the previous network expansion plan, we use the PIPSA in order to analyze projections. As you could see here, is a result in the difference between historical and representative concentration pathway for future scenarios. We see that if we calculate the expansion plan with historical, we are too optimistic, meaning that we overestimate the capacity, the transmission capacity, meaning that now we need to spend more money, spend more investment in the future using the representative concentration pathway. The second result that you see here is now the same test case, but this time the RCPs are not using only to modify the rating, but also to influence the profile of load and renewables. So we could see here, there are 2 lines that are congested. In the bottom part, right part, we see that the climate will reduce the ratings. But remember that this is a risk control. So here, the reduction is not only by the weather, it's also by the expansion of the grid, depending of the network expansion planning accordingly to RCPs. The second part here is if we plan with historicals, we are too optimistic. So meaning that we overestimate the capacity, meaning that in historical we don't need investment. However, as we could see here with the RCP scenario, we need it. So here are the full landscape of the previous result and the historical one. So in this full landscape, we see 2 things. Thinner temporal resolution using QTTR allow me to reduce the investment. And second, when we evaluate our network using historicals, we continue being too optimistic about the results, and we overestimate the rating capacity. So for that reason, we see that the investment started to increase using the specific scenarios. As a summary, my motivation here was involve the climate change inside the 2 methodological results previously. The contribution is the integration of climate projection inside the RCP and in the other methodology that is more constrained temperature based. To highlight, capacity will reduce over the 3 scenarios by the temperature, and also even if we use the risk control. And the third one that's also really important, if we use historical, we are doing a too optimist result as a scenario. For that reason, we must include the future projection condition in order to plan. So, conclusions and perspective. So, I show you my 3 subjects that are going to be interact and the results here. How can we calculate in advance the rating using the spatial variability of the weather? The result is QTTR new definitions. With this QTTR new definition, we not only maximize the capacity, but also we control the risk. And for example, in in this, we analyze the Danish region. We could even increase the capacity over 22%. The second, how we're going to integrate the QDTR, we analyze a network expansion plan in modifying the maximum capacity inside the optimization problem using QDTR. And the second is the risk control management method. That is a new method in order to include the temperature and let us to expand a new tolerated risk areas to calculate, to modify the maximum capacity inside the optimization. And also important see here is the influence of PV. The influence of PV, if we use QDTR, that led me to highlight this dangerous zone that is not only by the weather, but also by the flow. Third one is climate change. As we could see before, the climate will impact all the three components. If we analyze as a European continental scale, power transformer will be the most influenced one with a reduction of 2.1. And the third one is really important. It's like we don't have to plan with historical. We need to include the climate change inside our optimization in order to plan in the future our networks. Perspective, of course, there are so many perspectives. First of all, it's important to update to new climate data set that let us to identify more regions. And now with, for example, with socio-economical pattern. Second, in the same one, as we did with underground cables, in order to improve the variability of the soil temperature and moisture, we could do it with wind, for example, in order to improve the data set. Second thing over here is, as you could see here, all my results have been done with one specific climatic scenario. In order to be more precise with the uncertainty, we could include a multi-model ensemble, so different kind of climate models in order to assess the capacity. That one, incorporate the sensitivity analysis across available climate support in order to have a better selections. The introduction of a COPF now, because we started to scratch distribution, so it's important to calculate the losses inside the optimization. This is because the Monte Carlo solution is our first contribution, but we know that in terms about computational times, it's not the best one. So now I'm working on another research in order to introduce chance constraint inside the optimization, but also we could pass over robust optimization if necessary. And the last one is moving from transition power system, use the QDTR, but now with the thermal generator. So that means so that, for example, the profile of the thermal side of the generator could be analyzed with the QDTR. Dissemination. So 3 journals that have been published, and 3 that mostly coming in the next month. One is 99% with. The other is 80% that you see all the results about the last methodology. And now the last one is 10% that is about the chance constraint inside the power, inside the optimization. And 2 international conferences also. So this is all my results, and thank you, and sorry about the sound and everything about the sound.